everyone, today we are going to talk about non-homogeneous linear systems. This is section 5.7 of the textbook, and we will learn how to solve them. So I start with definitions. The non-homogeneous linear system is the system of this form. X prime is something linear of x, and then something that only depends on t. This B is called the non-homogeneous term, and this is a homogeneous part. Now this is a system, so X is a vector and B is a vector and A is a matrix, n by n matrix. So today we are going to assume that this A doesn't depend on time, though the method applies to the general case. So for example, we can take this particular system. Here this first part is a linear part, so the matrix A, the matrix of coefficients, is 2, 1, 3, minus 1. Here it is, 2, 1, 3, minus 1. And B is this part that only depends on t and does not involve x1, x2. It is 1 tangent t. So B is a vector function 1 tangent t. Our today's method, called variation of parameters, will apply to this system. First of all, we should start with a homogeneous system, so you should throw away this term bt and only look at x prime equals ax. You know how to solve this using the eigenvalue method, and the short formula for the general solution is psi multiplied by constant vector, where psi is a fundamental matrix. Its columns are solutions. So first of all, I'm going to substitute x into this equation and get a useful formula on psi prime. So I substitute x into the equation x prime equals ax, but my x is psi c, so psi c prime is a psi c, x prime equals ax. Now I differentiate the left hand side. C is constant, c prime is 0, so that's what I get. And this equality holds for any constant vector c, because this is a general solution for any c. Okay, since this holds for any c, then the two matrices psi prime and a psi are equal. So there is a useful relation on any fundamental matrix. Its derivative is equal to a multiplied by psi. We will use it in the variation of parameters. Okay, now we pass to the non-homogeneous system with bt over here. The solution of the homogeneous system was psi c. We will vary this parameter c and replace it with a function. So we will try to find the solution in the form psi multiplied by c that depends on t. We already know what psi is. Psi is the fundamental matrix for the homogeneous part, and we are going to find c. So I'm going to substitute this into the equation, as I already did when c was constant, but now it is not constant. So the left hand side is x prime, the right hand side is ax plus b, and in the middle I differentiate this left hand side using the product rule. This is psi prime c plus psi c prime should be equal to the right hand side. This is my equation that should hold for c. Now this equation seems more complicated than the initial one, but actually it is simpler, because if you look at this formula, psi prime equals a psi, you will see that the first terms of the equation cancel out. This term is equal to this term. The only terms that are left is this term and this term, and now we have a simple condition on c prime. We can express c prime from this formula like that. C prime is psi to the power minus 1 multiplied by b, and this is a formula for c. So B is a vector and non-homogeneous part. Psi is a matrix. Psi to the power -1 is the inverse matrix, inverse to the fundamental matrix. And this is your condition on the vector C. Now x is psi multiplied by this C that you can find from this equation. Okay, so this is the variation of parameters method. I'm going to write out the resultant formula. I'm going to find C using this equation. To do this, you just integrate both sides. So I'm going to take this and integrate both sides. That's what I do. This is my formula for C. For any equation of this form, any non-homogeneous linear equation, the solution has this form. And C is a vector, this B is a vector, and this is a matrix. So this thing inside the integral is a vector. When you integrate it, you should integrate each component. This is arbitrary constant. C0 is arbitrary constant vector. And now we get a formula for x that is a little bit hard to remember, so maybe it is easier to remember this formula and remember that x is psi multiplied by C. This is our formula. It actually applies to the more general case when A depends on T, when the linear part depends on T. But before you can use it, you should compute the fundamental matrix, which is hard when A depends on T. So we are not going to do this in the course. Now I wanted to draw attention to this C0. Please don't forget the integration constants, because if you forget them, you only get one solution, and you actually want the general solution. You want many solutions. So please don't forget this vector C0. Now, this formula can become a little bit simpler if you use the matrix exponential in place of the fundamental matrix. From the previous class, you know that the matrix exponential is a particular case of the fundamental matrix. So you can choose psi equals e to the power at and substitute it here. This could be a shortcut because the matrix exponential is easy to reverse. Its inverse is just e to the power minus at. But sometimes this shortcut is not really good, because first of all you will have to compute the matrix exponential, and sometimes it could be technically difficult. So you can choose either you use just any fundamental matrix or you compute the matrix exponential. This is up to you. Okay, so let's have an example of the variation of parameters method. I chose this linear system. This is 1 over sine here. This is the linear part, so the matrix of coefficients is 0, 1, minus 1, 0, 0, 1, minus 1, 0, and the non-homogeneous part is 0, 1 over sine. First of all, we need to know what psi is. You should solve the homogeneous equation, remove b, and just solve x1 prime equals x2, x2 prime equals minus x1. Solutions are, the eigenvalues are I and minus I. Solutions are combinations of sine and cosine. So this is a general solution of the homogeneous equation. Now I can write this as psi multiplied by c. This is my fundamental matrix psi. Its columns are solutions of the equation. This solution is the first column, and this solution is the second column. And this is my fundamental matrix for the homogeneous part. Now I need to invert this matrix. Luckily, this matrix is actually equal to the matrix exponential, so it will be easy to invert. It is equal to the matrix exponential because the matrix exponential is the fundamental matrix whose value at 0 is 1, the unit matrix. So if you substitute equals 0, you will see that this matrix is a unit matrix. So this is actually, this fundamental matrix is the matrix exponential, e to the power at. So you can just invert it using this formula, and you just substitute minus t instead of t here to compute e to the power minus at, and this is your inverse matrix. In general, you will have just to invert this matrix, fundamental matrix, treating t as a parameter. But here we had a shortcut. Now, since we know psi and psi to the power minus 1, we can just apply the formula. So this c is a constant vector plus fundamental matrix to the power minus 1 applied to the non-homogeneous part, this b. Then you should multiply this matrix by a vector, that's what you get. And then you integrate this vector, which means that you integrate both components of the vector. This logarithm of modulus of sine is the integral of cotangent. And the vector c0 will have components c1 and c2. So c1, c2 is this vector c0 over here. And now x is psi by c. You should multiply your psi by this vector c, and whatever you get is your solution. So that's how you apply the variation of parameters method for non-homogeneous equations.